Today we are going to discuss on Unit 10 the sBlock elements. So sBlock elements, okay, let's see what are those. So sBlock elements are those in which the last electron enters the outermost s orbital or valence shell. By valence shell we mean the outermost shell, okay. So in sBlock elements, okay, the last electron, okay, the last electron will enter s orbital, okay. So we all know s orbital, okay, s orbital. So in s orbitals it can have up to 2 electrons, okay, 1 2, okay. So if there is 2 electrons, we denote it by s2, okay. Let's take it as n, okay. So we don't know the exact principal quantum number or in which shell it is, so let's denote it by n. It can have either 2 electrons or 1 electron. S2 and ns1, okay. So there is 2 possibility, okay. Either it can be ns1 or ns2. So when it is ns1 configuration or electronic configuration with ns1, this makes the group 1 element, okay, and for ns2 group 2 elements, okay. So sBlock elements can have 2 group, okay, group 1 and group 2, depending on the number of electrons in the s orbitals, okay. The outermost s orbital, okay, we are talking about the outermost s orbitals. In the outermost s orbital, if there is 1 electron, it means it belongs to group 1 elements. If it is 2 electrons, it belongs to group 2 elements, okay. So group 1 elements, they are also called alkali metals. Group 2 elements, they are also called alkaline earth metals. We'll discuss about that later also. Let's see the periodic table. Okay. In your periodic table, these are group 1 and group 2 elements, okay. So group 1 and group 2 elements are here. So they are sBlock elements, okay. So this periodic table is also arranged according to the orbitals, okay, s, p, d, f orbitals, okay. So for s, the last electron will enter s orbitals, okay, and for d, the last electrons will enter d orbitals. For p, the last electrons will enter p orbitals, and for f, the last electrons will enter f orbitals, okay. So in this way, periodic table is also arranged according to the orbitals, okay, s, p, d, f. Now we come back here. So group 1 elements, okay, consists of lithium, sodium, potassium, rubidium, cesium, francium. And group 2 elements consist of beryllium, magnesium, calcium, strontium, barium, and radium. So sBlock elements, they are divided into group 1 and group 2, okay. Now let us see the electronic configuration. For lithium, we know that atomic number is 3, okay. So lithium atomic number 3. Before going to electronic configuration, let's see the atomic numbers, okay. So if you remember this atomic number of the fourth element, okay, there is a shortcut to remember the atomic number of the rest also, okay. So Suppose lithium is 3, so if you add 3 with 8, okay, 8 8 18 18 and 32. So if you add 3 plus 8, it becomes 11, okay. 3 plus 8 11, 11 plus 8 19, okay. 19 plus 18 37, okay, 55 and 87, okay. So if you add 3 with 8, this will give the atomic number of sodium, okay. So if you remember the first one, you can add it with 8 8 18 18 and 32, okay. This will give the atomic number of the rest, okay. So this is also a shortcut way, okay, for easy understanding. Now let's see the electronic configurations. So atomic number 3, electronic configuration, as we have discussed before, it will be 1s1 2s1, okay, or we can write it in shortcut form, okay, or helium 2s1. So we are bringing the noble gas, okay, noble gas configuration here. So those noble gases, okay, are neon, argon, krypton, xenon and radon, okay. So these are the noble gases, okay. So it will start from helium, neon, argon, krypton, xenon and radon. So in place of this 1s2, we write helium, okay, helium atomic number 2. So helium cover this part, okay. So for the second one, we will just write the shortcut form. So we write neon 3s1, and then argon 4s1, next krypton 5s1, next xenon 6s1, after that radon 7s1. So it will be, this is the shortcut form. Either way you can write the long form also, okay, no problem with that, okay. So this shortcut form you write in order to save time also, okay. Either way you write, you can write the long form, short form, it depends on you. Similarly for this one, okay, you can, if you know the atomic number of barium, you can add, okay, that atomic number with 8, okay, following the same step, okay. You can write the electronic configurations, okay. So for this one with helium 2s2, so we are simply writing directly for this one 3s2, argon 4s2, krypton 5s2, xenon 6s2, indium 7s2. Suppose if you write the electronic configuration, the first of full electronic configuration for sodium, okay, it will be 1s2, 2s2, 2p6, okay, 3s1, okay, 11, so 1, okay. So we are writing there for this 10, so become neon, so we write neon. Then outermost, okay, after neon we are writing the outermost shell after neon, okay, representing it by 3s1. So from here, okay, we can write the general electronic configuration. General electronic configuration of group 1 element is NS1. Okay, NS1. Okay, the outermost shell. And for this one, group 2 elements, I'm writing in short for general electronic configuration will be NS2. Okay, so this is the electronic configuration. So this group 1 elements, let's represent it by M, okay, plus H2O. So they react with water to give metal hydroxide. Okay, OH, we know. Okay, it is named as hydroxide, metal hydroxide. Okay, or they react with water to give hydroxide. Okay, therefore they are also alkaline in nature. Okay, that's why they are called alkali metals. Now for this one, okay, except beryllium, okay, except beryllium, so these elements, okay, are called alkaline earth metal. Okay, alkaline earth metal. Because they are oxides, okay, and hydroxides. Their oxides and hydroxides are alkaline. Their oxides and hydroxides are alkaline. That means basic. Okay, they are basic. Okay, they are found in Earth's crust. Okay, found in Earth's crust. Now this one, this sodium and potassium, okay, are more abundant. This sodium and potassium are more abundant than the element in their respective group. Okay, and this magnesium and cesium, okay, they are abundant, okay, than the rest. Okay, so among the in the periodic table, this rank 5th, okay, 5th and 6th. Okay, magnesium and calcium rank 5th and 6th, okay, in abundance. Now this francium is radioactive. This is radium, it is also radioactive. Okay, so we won't discuss much about francium, okay, since it is radioactive in nature. Okay, so this francium has isotope, okay, 2, 3. Francium isotope, okay, this isotope have half-life of 21 minutes. Okay, so it will decay within in 21 minutes. Okay, so that's is general introductions, okay, of sBlock elements. Now let's discuss the general characteristics of group 1 elements. So group 1 elements, as we have discussed, they are also known as alkali metals. Okay, now electronic configuration, we have already discussed the electronic configuration. Okay, So I'm writing in short form. Okay, general electronic configuration is NS1. So this NS1 means they have only one electron. Okay, so they readily, that means easily lost. Okay, one electron, this one electron, okay, from outermost shell to become electropositive. Okay, so N plus ion. Okay, so they are also known as electropositive elements. Okay, and they are highly electropositive. Okay, so since they are electropositive, okay, they usually exist, they don't exist freely. Okay, now atomic and ionic radii. So as we move down the group, okay, when we move down, okay, atomic number increases. Therefore, when atomic number increases, size also increases, and number of shell, okay, this shell also increases, okay, with the increase in atomic number. Okay, so as the size increases, okay, this atomic radii will increase. Okay, and ionic radii means suppose lithium. Okay, if you remove one electron, then it becomes Li plus. Okay, so this is ionic. Okay, when an element lost an electron, okay, and become positive charge or either negative. Okay, so it lost one electron and become Li plus, so this is ion. Okay, Li ion, lithium ion. Okay, so when it lost one electron, okay, it becomes smaller than the original Li. Okay, the parent element. Okay, size decreases than the parent element. Okay, so if you compare all the Li Na plus, okay, this Na will have larger size than Li. Okay, so as we move down the group, the atomic and ionic radii, it increases. Okay, increases down the group. Now ionization enthalpy. So this ionization enthalpy is the energy, okay, required to remove the outermost electron. Okay, from the outermost shell of a gaseous atom. So see, suppose the electron is present at the outermost shell. Okay, so the distance between the nucleus and the electron, it increases, and therefore there is less attractive force between the electron and the nucleus. Okay, and electron will be present in the inner shell also. So this electron, okay, act as a shield towards the outermost electron. Okay, and they repel this electron away from the nucleus also, and this inner electron act as a shield towards the outermost electron. Okay, so as we move down the group, okay, down the group, size increases, okay, and shield increases. Okay, therefore the shielding also size increases. Okay, shell also increases, shielding effect increases down the group. Therefore ionization enthalpy will decrease. Okay, down the group. Okay, since it will require less energy, okay, to remove the outermost electron, okay, if the size is big. Okay, if the size is small, there is much attractive force between the electron and the nucleus, okay, since electron is closer to the nucleus. Okay, so smaller size will require higher energy to remove electron. Okay, so as we move down the group, size increases. That means it becomes easy for the electron to be removed. Now, hydration enthalpy. So this hydration enthalpy, okay, is the energy release when one mole of gaseous ions combined with water to form hydrated ions. So when one mole of gaseous ion combine with water, okay, okay, so when it combine with water, the energy release is the hydration enthalpy. Okay, so smaller ions, okay, will have higher ionization, not ionization, sorry, hydration enthalpy. So the reason I will discuss now. Suppose this is the cation, okay, so we all know nucleus, okay, there is proton in the nucleus. Okay, so smaller size means the size is smaller, okay, and nucleus, okay, this nucleus can attract, okay, other ions, okay, or even electrons. So let's say anions, okay, so this cation, okay, can attract this negative charge or anion, okay, because it is smaller, okay, and the nucleus of this can attract. Okay, suppose we take a bigger cation, okay, and anion. So bigger cation means shell, okay, there is a number of shell, okay, so this, for this cation to attract electron, okay, or electron clouds become difficult, okay, since they are bigger in size. So for smaller size, they can easily distort, okay, distort this cloud. They can distort this cloud, okay, like this, okay, this distortion, okay, so it is known as polarizing also. So there is another rule, okay, known as Fajan's rule, okay. So according to Fajan's rule, okay, when ionic size increases, polarizing power decreases, okay, and therefore energies to attach water molecule also decreases. Okay, so bigger size means polarizing power decreases. Okay, polarizing power means the power to distort these electron clouds. Okay, now let's come here. So lithium with a smaller size will have the highest polarizing power, so it can, or it will have the highest hydration enthalpy. Li plus, Na plus, Aa plus. So it decreases, okay, when we move down the group, okay, decreases. So Li example, okay, Li from hydrated ions, okay, example is LiCl2H2, okay, and this is the only element, okay, in group 1 which form these hydrated ions. Now physical properties. So alkali metals, they are silvery white, okay, soft and light metals, and since they have large size, okay, they have low density, okay, and increases in the order Li greater than Na, okay, Li less than Na, but except for this one, potassium, okay, potassium has a higher density than sodium, okay, don't forget this one. And then rubidium greater than K, okay, density greater than K, cesium greater than rubidium. Now they have low melting and boiling points, okay, so the reason is their metallic bond is weak, okay. Why this metallic bond is weak? Because they have only one electron in the outermost shell, okay, or valence shell, okay. So weak bond, okay, weak bond means this bond can break easily, okay, and if this bond break easily, that means they will melt easily or boil easily, okay. Strong bond means it will take time to melt or boil, okay. Now the alkali metals and their salts impart characteristic color, okay, to an oxidizing flame, okay. So these alkali metals, okay, if we heat them, they show colors, okay. This is also known as flame taste, okay, and they can also be determined by flame photometry, atomic absorption spectroscopy. So now let's see flame, okay, flame applied, okay, when we apply to this alkali metal, okay, when we apply flame to this alkali metal, their electron, okay, they are in ground state, okay, I'm writing in short form ground state. The electron absorb energy and move to excited state, okay, excited state. So after absorbing this energy, okay, after some time they release this energy, okay, and come back to ground state, okay, from excited state to ground state, okay. So while coming back, okay, they release this energy, okay, energy or radiation, okay. So they release this energy or radiation in visible spectrum, okay, of electromagnetic spectrum, okay. So these are visible, so when they release this energy, since they are in the visible region, we see colors, okay, they show colors, okay, that is the reason, okay. So lithium show crimson color, okay, crimson red, sodium yellow, potassium violet, rubidium red violet, cesium blue. So when we heat these elements, they show these colors.